In the next few slides, I just wanted to introduce and describe how we solve the heat equation numerically. And I also wanted to begin by just giving you sort of I called it an informal interpretation of what we mean by Laplace's Poisson's equation, what we mean by the heat equation, diffusion equation, what we mean by the Laplacian operator in space or space-time, what that operator does in space or space-time. So the Laplacian operator figures the difference, represents the difference, or computes the difference between a function, say the electrostatic potential, at a point, and the average of that function at neighboring points. So if we imagine this discrete space here on the left-hand side, the Laplacian operator will represent the difference between the value of the function here at xy and the average value of these four neighboring space points. So that's what the Laplacian operator does. In Laplace's equation, it says that that operation is equal to 0, which means that Laplace's equation describes a function, describes, say, an electrostatic potential, whereby the value of that electrostatic potential at this point here, xy, is equal to the average of these four neighboring points. So that's what Laplace's equation means. And it ensures that statement about the value of the function at the point xy being equal to the average of the neighboring points is true everywhere throughout the region of space, which the Laplace equation is applicable to. In the case of Poisson's equation, the Laplacian isn't 0 in general. It's equal to the charge density at each point in space, or charge density divided by epsilon naught, each point in space. So in that particular case, what the Poisson's equation is enforcing or dictating is that the potential at this xy point here in green is different from the average value of the potential at the four neighboring points in magenta, is different by an amount that corresponds to the charge, I'll call it delta Q or dq, at this point here, divided by epsilon naught. So if there's no charge here, then this potential is the average of the neighboring points. If there is charge here, it's different from the average of the neighboring points in proportion to that amount of charge. So it could be bigger or smaller, depending on whether the charge at that location is positive and negative. And it could be much bigger or just a little bigger, depending on whether the charge at this location is just a small amount of charge or a much bigger amount of charge. So that's how to visualize the Laplacian operator, how to visualize Laplace's equation, how to visualize Poisson's equation in a discrete space. So I also wanted to say a few words about visualizing the Laplacian operator in the heat equation, diffusion equation, and also visualizing the heat diffusion equations themselves. So in this little sketch over here on the left-hand side, I'm imagining horizontally position and vertically time. So now this is space and time. I'm going to imagine this point in green here, this space-time point in green, where the function u describes the temperature at this point. To the left and the right are at the same time two neighboring points, and upstairs and downstairs are the same location, but the temperature at an earlier time and a later time. As we said, the Laplacian operator represents the difference between, or computes the difference, or evaluates the difference between the value of the function at this particular location in green here, x, and the value at the neighboring points, the average of the value at the neighboring points. So the one over here on the left, the one over here on the right. That's what the Laplacian operator evaluates. If in our case, say the diffusion equation said that the Laplacian of the temperature was equal to 0, that would be the case when no heat is flowing in or out of this point here. That would correspond to this green point literally being the average of these two neighboring points. And that's the case when no heat is flowing, no net heat is flowing into this green point, no net heat is flowing out of this green point. We're in sort of a steady state at this green point. If in the heat diffusion equation, the Laplacian of the temperature is not equal to 0, that's where the rate of change of the temperature is in time is not equal to 0, then this green point here, its temperature is not the average of the two neighboring points. And it's not the average of the two neighboring points because the temperature is changing with time. It's, for example, getting hotter as we go to later times, or getting cooler as we go to later times. There's a change in temperature at this point between the earlier time downstairs here, the later time upstairs here. So that's a case where there is net heat flowing and the temperature will be changing at that point. So that's how to visualize the heat equation, diffusion equation, and Laplacian associated with the heat diffusion equation for discrete space and time. So now I want to move on to how do we implement a heat equation to obtain a numerical solution to a particular thermodynamics heat flow problem. So I want us to think about this example. In this example, I've got a glass window here in gray. Upstairs here is indoors inside the house, so a cozy 24 degrees Celsius. And outside, downstairs here, this is outdoors, a cool 0 degrees Celsius. Now I've arranged that initially the glass was at 10 degrees Celsius, the indoor temperature was 24 degrees Celsius, and the outdoor temperature is 0 degrees Celsius. We're going to imagine that the indoor temperature doesn't change. We're going to imagine that the outdoor temperature doesn't change, but rather this 10-degree uniform temperature of the glass, that will change with time. For example, the side of the glass that's inside the house will warm up. The side of the glass that's outside the house will cool down. And we want to solve the heat equation to find out exactly how the glass warms up, cools down, develops a temperature gradient from the inside to the outside of the house. Now, again, intuition tells us what this solution will look like. I've sketched over here on the right-hand side my intuition about this situation. So this top graph here is the initial condition. Inside the house, 24 degrees Celsius. Outside the house, 0 degrees Celsius. The glass initially is at 10 degrees Celsius throughout its thickness. Now, I don't know how I prepared that, but somehow I magically prepared that, but that's the initial condition pictured in this graph. Now, what happens? So for later times, we know what's going to happen. On the warm side of the glass, heat will flow into the glass. It's 24 degrees Celsius, warmer than the glass. On the cool side of the glass, heat will flow out of the glass. It's colder outside the glass on the cold side. And so we're going to get heat flow in on the warm side, out on the cool side. The warm side of the glass is going to increase its temperature. The cool side is going to decrease its temperature. And we'll start to see this sort of temperature profile. So here you see on the side that's on the indoors of the glass, its temperature has risen above 10 degrees Celsius. On the side that is on the outside of the house, then the temperature there is decreasing as heat flows out. And with time, we would expect this flow of heat through the glass to continue, and ultimately it will continue to get until you get a steady state. You get a steady state where the temperature gradient through the glass is just this constant gradient from the warm 24 degrees inside to the 0 degrees outside. Now that's all intuition. That's what I think will happen. That's what my everyday experience says will happen to the glass. Now let's apply the heat equation numerically and see if we can calculate exactly what happens. In particular, what my intuition doesn't tell me is how long this thermalization will take. How long does it take to reach this steady state of flow of heat through the glass window from the inside of the house to the outside of the house? Okay, so now I want to describe the rewriting, the reformulation of the partial differential equation, that is the heat equation or diffusion equation, as a difference equation. So as an equation that we can use in a discrete space-time where we don't have continuous space coordinates, we have discrete space points. Where we don't have a continuous time coordinate, we have discrete time points. So I pictured that over here on the left-hand side for my pane of glass, my window of glass. This red line here is the side of the edge of the glass that's in the house. This blue line here is the side, the edge of the glass that's outside of the house. So this is the cold side at the bottom. This is the warm side at the top. And this lattice here, each intersection here is a point in space from the inside of the glass to the outside of the glass, over which I'm going to calculate the temperature profile. So that's the vertical direction. Horizontally, I'm imagining this horizontal axis is the time axis. So over here on the far left, this is the initial conditions of the glass. Remember, the initial condition was that the glass was at 10 degrees Celsius. And then as we walk from the left, the glass everywhere being 10 degrees Celsius, towards the right, the temperature of the glass across the width of the glass is going to change with time. And so as I step here, this is the next time interval. Step here, this is the next time interval. Step here, this is the next time interval, and so on and so forth for this particular location in the glass. And downstairs here, near the outside of the glass, this is the initial time. This is the next time. This is the next time. This is the next time for that particular location in the glass. So we're dividing the glass up into a series of space points, and we're just dividing time up into a series of time points. I've called A the lattice spacing in space, and I've called H the kind of the lattice spacing in time. So A is a distance interval between 2 points in space, and H is a time interval between 2 points in time. We've got to make a difference equation of the heat equation by rewriting the differential with respect to space as a difference equation, rewriting the differential with respect to time as a difference equation. So let's go ahead and do that. I did it in two parts. One part on this slide for the space part, the other part on the next slide for the time part. So let's just see these two parts. So first step, I want to rewrite this partial differential with respect to the space coordinate. I want to rewrite that as a difference equation, and here it is. So this is a second order differential that measures the curvature, and using the Taylor expansion, you can rewrite that as this equation here. So this involves the temperature at some point at x and the temperature at neighboring points x plus a and x minus a, and this combination determines the curvature of the temperature, or this second order partial differential. And again, this a here is this lattice spacing of these space points. So I can take this equation here, this difference equation, and replace in the heat equation the second order partial differential with respect to x with that equation. And I did that down here. I just fed it in to the heat equation. Now I want to do the same thing for the part of the heat equation that describes the time dependence, has the differential with respect to time. So again, this is a matter of using the Taylor expansion to replace the differential with respect to time. It's a first order differential in terms of a difference equation. So because the space time differential is a first order differential, the space differential is a second order differential, the time differential probes the slope of the solution to the equation, the function that is described by the equation as a function of time. For the case of the spatial variation, the second order differential was probing the curvature of that function of space coordinates. So the replacement's a little different. It's a little simpler here. The rate of change of the temperature as a function of time is simply, at some given point, is simply the value of that temperature at a certain time t, and its difference with the value at that certain point at a time one step later, so t plus h. And again, this h here is the lattice spacing of our time coordinates. So I can plug this second equation into the heat equation. I did that downstairs here. I rearranged things a little bit. And the reason I rearranged it is that I wanted to make this equation read in the following way. So this equation tells you the temperature at a particular location x at a time t plus one step in time, t plus h. And it tells you the temperature at this later time, t plus h, in terms of the temperature at that point at an earlier time, the earlier time, and also the temperature at the two neighboring points to the left and right at the earlier time. So this allows you to calculate the temperature at a later time from the temperature at earlier times. And this is why we call this method the leapfrog method. It allows us to calculate, if we know the temperature on the gas pane initially, we can calculate the temperature one step later. And then if we know the temperature one step later, we can calculate the temperature two step later. And you can just do this iterative process of calculating the temperature profile one step after the next step after the next step. And this is the leapfrogging. This is the leapfrogging method, leapfrog method. And so this is the equation that we're going to use, the difference equation that we're going to use to solve the heat equation. It has some resemblance to the difference equation that we used for the Laplace's equation, but it's clearly not the same equation. In Laplace's equation, we had a two-dimensional space, and we had neighboring points to the left, right, and upstairs and downstairs. In this difference equation, we got a one-dimensional space, just points to the left and right, and then we've got times that are earlier and later, temperatures that are earlier and later. In this equation, we're trying to see how the temperature dependence of the rod evolves. In the Laplace equation, we were trying to figure out how the XY space dependence of the electrostatic potential evolves.